Okay, so today this lecture is going to be on atoms and molecules, delivered by me, Neil Faulkner, with a bachelor's degree in business management. First of all, just wanted to cover off what we're covering today, just looking at the contents. So, matter consists of chemical elements in pure form and in combinations called compounds. So we'll be looking at the difference between the elements in the periodic table, and then we'll be looking at how they can combine to create compounds. An element's properties depend on the structure of its atoms. The formation and function of molecules and ionic compounds depend on chemical bonding between atoms. So it's these chemical reactions that make or break bonds. So first of all, we're going to look at how matter consists of chemical elements in pure form and in combinations called compounds. Matter is said to made up of elements. So if we take, for example, like the table that we're currently sat at, or a piece of furniture, that is matter, and that's made up of elements, of which there are currently 92 known by scientists. With reference to the periodic table, each element has a symbol, usually the first letter or two of its name. A compound is a substance consisting of two or more different elements combined in a fixed ratio. Table salt, for example, is sodium chloride, a compound composed of the elements sodium and chlorine in a 1-to-1 ratio. Pure sodium is a metal and pure chlorine is a poisonous gas. However, when combined, they form an edible compound. Water is another example of a compound that consists of the elements hydrogen and oxygen in a 2-to-1 ratio. So although water is matter, it's actually made up of elements, and those elements are hydrogen and oxygen. These are simpler examples of organised matter having emergent properties. So take, for example, wood, which originates from trees, and trees come about through photosynthesis. It's often said that a compound has characteristics different from those of its elements. So, for example, if you took a table, for example, made up of wood, by the time it gets to us at home, it may have a shiny coating on it. It may also have plastic on the bottom of its legs to stop it sliding around. These means that the compound has characteristics that are different from its original form. Of the 92 elements that exist, about 25% are essential elements that an organism needs to have a healthy life and reproduce. The essential elements are similar among organisms, but there is some variation. Humans need 25 elements, but plants only need 17. Just 4 elements, oxygen, carbon, hydrogen, and nitrogen, make up about 96% of all living matter. Calcium, potassium, phosphorus, and sulfur, and a few other elements account for most of the remaining 4% or so of an organism's mass. Trace elements are required by organisms, but only in minute quantities. So basically what we're saying is that 4 elements that we need to know are oxygen, carbon, hydrogen, and nitrogen. And it's these 4 elements that make up 96% of all living matter. The remaining 4% is made up of calcium, potassium, phosphorus, and sulfur. And of course a few other elements which are called trace elements. Iodine is an example of a trace element, and is an essential ingredient of a hormone produced by the thyroid gland. An iodine deficiency in the diet causes the thyroid gland to grow in size, a condition called goitre. Consuming seafood or iodized salt reduces the incidence of this. Some naturally occurring elements are toxic to organisms. In humans, for instance, the element arsenic has been linked to numerous diseases and can in fact be lethal. In some areas of the world, arsenic occurs naturally and can seep into groundwater, As a result, millions of people are being exposed to arsenic-laden water. Efforts are underway to reduce arsenic levels in their water supply. An element's properties depend on the structure of its atoms. So when we look at matter, we look at the elements that make up the matter, and each element consists of a certain type of atom that is different from the atom of any other element. So atoms are the smallest unit of matter that still retain the properties of an element. We symbolize atoms with the same abbreviation used for the element that is made up of those atoms. Although the atom is the smallest unit of the properties of an element, these tiny bits of matter are composed of even smaller parts called subatomic particles. Scientists use high-energy collisions to produce 100 types of particles from the atom, but to be honest, for GCSE and A-level, only 3 kinds of particles are relevant here, and these are the neutrons, the protons, and the electrons. Protons and electrons are electrically charged. Each proton has 1 unit of positive charge, and each electron has 1 unit of negative charge. A neutron, as its name implies, is electrically neutral. The neutron and proton are almost identical in terms of mass, each about 1.7 times 10 to the power 24 grams. Grams and other conventional measurements are not very useful for any such tiny pieces, but is referred to as the atomic mass unit. Although the atom is the smallest unit of the properties of an element, just to recap, these tiny bits of matter are composed of even smaller parts called subatomic particles. So scientists use high-energy collisions to create these subatomic particles. However, that's far too much detail for what we need to cover. There are only really 3 kinds of particles that are relevant here, and these are the neutrons, the protons, and the electrons. Protons and electrons are electrically charged. Each proton has 1 unit of positive charge, and each electron has 1 unit of a negative charge. A neutron, as its name implies, is electrically neutral. The neutron and proton are almost identical in terms of mass, each about 1.7 times 10 to the power 24 grams. Grams and other conventional measurements are not very useful for tiny pieces of matter, so we use a scientific term called the atomic mass unit. Atoms of the various elements differ in their number of subatomic particles. All atoms of a particular element have the same number of protons in their nucleus. The abbreviation 2He tells us that an atom of an element, helium, has 2 protons in its nucleus. Unless otherwise indicated, an atom is neutral in its nucleus. Again, unless otherwise indicated, an atom is neutral in electrical charge, which means that its protons must be balanced by an equal number of electrons. Therefore, when we look at the atomic number, it tells us the number of protons and also the number of electrons in an electrically neutral atom. We can also deduce the number of neutrons from the second quantity called the mass number, which is the total number of protons and neutrons in the nucleus of an atom. Since the atomic number indicates how many protons there are, we can determine the number of neutrons by subtracting the atomic number from the mass number. The number of neutrons equals the mass number, take away the atomic number. All atoms of a given element have the same number of protons, but some atoms have more neurons than other atoms of the same element and therefore have greater mass. These different atomic forms of the same element are called isotypes of the element. In nature, an element may occur as a mixture of isotypes. For example, the element carbon, which has the atomic number 6, has 3 naturally occurring isotypes. The most common isotope is carbon-12, which accounts for about 99% of the carbon in nature. The isotope has 6 neutrons. Most of the remaining 1% of carbon consists of atoms of the isotope that has 7 neutrons. A third, even rarer isotope has 8 neutrons. But notice that all three isotopes of the carbon have 6 protons, otherwise they would not be carbon. Although the isotopes of an element have slightly different masses, they behave identically in a chemical reaction. So it's said that carbon-12 and carbon-13 are stable isotopes, meaning that their nucleus does not have a tendency to lose its subatomic particles, a process known as decay. The isotope carbon-14, however, is unstable or radioactive. A radioactive isotope is one in which the nucleus decays spontaneously, giving off particles and energy. When the radioactive decay leads to a change in the number of protons, it transforms the atom to an atom of a different element. Radioactive isotopes have many useful applications in biology. Radioactive isotopes are often used as diagnostic tools in medicine. The body's cells can use radioactive atoms just as they would use non-radioactive isotopes of the same element. The radioactive isotopes are incorporated into biologically active molecules, which are then used as tracers to track atoms during metabolism, the chemical process of an organism. For example, certain kidney disorders in humans are diagnosed by injecting small doses of radioactively labeled substances into the blood and then analysing the tracer molecules excreted in the urine. Radioactive tracers are also used in combination with sophisticated imaging instruments such as a PET scanner that can monitor growth and metabolism of cancers in the body. Although radioactive isotopes are very useful in biological research and medicine, radiation from decaying isotopes can also pose a hazard to life because it damages cellular molecules. So the severity of this damage depends on the type and amount of radiation an organism absorbs. One of the most serious environmental threats is radioactive fallout from nuclear accidents. Doses of most isotopes used in medical diagnosis are relatively safe. So researchers measure collective decay in fossils to try and date past life. Fossils provide a large body of evidence for evolution, documenting differences between organisms from the past and these living in the present, giving an insight into species that have disappeared over time. While the layering of fossil fuels can be indicative of the age of the fossils, it cannot be completely relied upon, hence the use of radioactive isotopes. A parent isotope decays into a daughter isotope at a fixed rate, expressed as the half-life of the isotope, the time it takes for 50% of the parent isotope to decay. Each radioactive isotope has a characteristic half-life that is not affected by temperature, pressure, or any other environmental variable. Using a process called radiometric dating, scientists measure the radio of different isotopes and calculate how many half-lives in years have passed since an organism was fossilized or a rock was formed. Some isotopes have a very short half-life, measured in seconds or days, whereas other isotopes have a very short half-life, such as uranium, measured in billions of years. So some isotopes have a very short half-life, measured in seconds or days, whereas other isotopes have a very long half-life and they're measured in billions of years. Simplified models of the atom greatly exaggerate the mix of the nucleus relative to that of the whole atom. If an atom of a helium were the size of a football stadium, the nucleus would be the size of a pencil eraser in the centre of a field. Moreover, the elements would be like two tiny gnats buzzing around the stadium. Atoms are mostly empty space. When two atoms approach each other during a chemical reaction, their nuclei do not come close enough to interact. Of these subatomic particles, only electrons are directly included in chemical reactions. An atom's electrons vary in the amount of energy they possess. Energy is defined as the capacity to cause change, the instance during work. Potential energy is the energy that matter possesses because of its locations or structure. For example, water in a dam located on a hill has potential energy because of its altitude. When the gates of reservoirs, dams are opened and the water runs downhill, the energy can be used to do work, such as moving the blades of turbines to generate electricity. Because electricity has been expended, the water has less energy at the bottom of the hill than it did at the top in the reservoir. To restore the potential energy of a reservoir, work must be done to alleviate the water against gravity. So, i.e., we need to move the water back uphill, and that takes work, which uses energy. Electrons have potential energy due to their distance from the nucleus. The negatively charged electrons are attracted to the positively charged nucleus. It takes work to move a given electron farther away from the nucleus, so the more distant an electron is from the nucleus, the greater the potential energy. Unlike the flow of water downhill, where the potential energy changes in steps of fixed amounts, an electron is like a ball on a staircase. The ball can have different amounts of energy depending on which step it is on, but it cannot spend much time between the steps. Similarly, an electron's potential energy is determined by its energy level. An electron only looks at certain energy levels and not between them. An electron's energy level is correlated with its average distance from the nucleus. Electrons are found in different electron shells, each with a characteristic average distance and energy level. In diagrams, energy levels can be represented by concentric circles. The first shell is closest to the nucleus, and electrons in this shell have the lowest potential energy. Electrons in the second shell have more energy, and electrons in the third shell have even more energy still. Electrons can move between shells, but only by absorbing or losing an amount of energy equal to the difference in potential energy between its position on the old shell and that in the new shell. When an electron absorbs energy, it moves to a shell further out from the nucleus. For example, light energy can excite an electron to a higher level. When an electron loses an electron and thus energy, it falls back to a shell closest to its nucleus, and the lost energy is usually released to the environment as visible light or ultraviolet radiation. The chemical behavior of an atom is determined by the distribution of electrons in the atom's electron shell. Beginning with hydrogen, the simplest atom, the periodic table of elements shows the distribution of electrons for the first 18 elements from hydrogen to argon. The elements are arranged in 3 rows or periods corresponding to the number of electron shells in their atoms. The left to right sequence of elements in each row corresponds to the sequential addition of electrons and protons. Hydrogen's 1 electron and helium's 2 electrons are located in the first shell. Electrons, like all matter, tend to exist in the lowest available state of potential energy. In an atom, this state is found in the first shell. In an atom with more than 2 electrons, the additional electrons must occupy higher shells because the first shell is full. The second shell holds a maximum of 8 electrons. So when we look at electron orbitals, these came about in the early 1900s. The electron shells of an atom were visualized or of concentric paths of electrons orbiting the Sun. It's important to remember that each concentric circle represents only the average distance between an electron in that shell and the nucleus. In reality, we can never know the exact location of an electron. What we can do instead is describe the space in which an electron spends most of its time. The 3-dimensional space where an electron is found 90% of the time is called an orbital. Each electron shell contains electrons at a particular energy level, distributed among a specific number of orbitals of distinctive shapes and orientation. It's possible to think of an orbital as a component of an electron shell. The first electron shell has only one spherical orbital called 1s, but the second shell has 4 orbitals, 1 large spherical orbital, and 3 dumbbell-shaped orbitals. The elements of a hydrogen atom occupies the first 1s orbital, as do the 2 electrons of a helium atom. The 4 orbitals of the second electron shell can hold up to 8 electrons, 2 in each orbital. Electrons in each of the 4 orbitals in the second shell have nearly always the same energy, but they move in different volumes of space. The reactivity of an atom arises from the presence of unpaired electrons in one or more orbitals of the atom's valence shell. As you will see in the next section, atoms interact in a way that complete their valence shells. When they do so, it is the unpaired electrons that are involved. The formation and function of molecules and ionic compounds depend on chemical bonding between atoms. Atoms combine to form molecules and compounds. Atoms with incomplete valence shells can interact with certain other atoms in such a way that each partner atom completes its valence shell. The atoms either share or transfer valence electrons. These electrons usually result in atoms staying close together, held by attractions called chemical bonds. The strongest kind of chemical bonds are covalent bonds in molecules and ionic bonds in dry ionic compounds. So when we look at covalent bonds, a covalent bond is the sharing of a pair of valence electrons by 2 atoms. For example, let's consider what happens when 2 hydrogen atoms approach each other. Hydrogen 1 has 1 valence electron in the first shell, but the shell's capacity is 2 electrons. When the 2 hydrogen atoms come close enough for their 1s orbitals to overlap, they can share their electrons. Each hydrogen atom is now associated with 2 electrons, in what amounts to a completed valence shell. 2 or more atoms held together by covalent bonds constitute a molecule, in this case a hydrogen molecule. There are several ways of representing a hydrogen molecule. Electron sharing can be depicted by an electron distribution diagram or by a Lewis dot structure, in which element symbols are surrounded by dots that represent the valence electrons. We could use a structural formula where the line represents a single bond, a pair of shared electrons. A space-filling model comes closest to representing the actual shape of the molecule. Oxygen has 6 electrons in its second electron shell and therefore needs 2 more electrons to complete its valence shell. 2 oxygen atoms form a molecule by sharing 2 pairs of valence electrons. The atoms are thus joined by what is called a double bond. Each atom that can share valence electrons has a bonding capacity corresponding to the number of covalent bonds the same atoms can form. When the bonds form, they give the atom a full complement of electrons in the valence shell. The bonding capacity is called the atom valence and usually equals the number of atoms required to complete the atom's outermost valence shell. So the molecules of hydrogen and oxygen are pure elements rather than compounds, because a compound is a combination of 2 or more different elements. Water with the molecular formula H2O is a compound. 2 atoms of hydrogen are needed to satisfy the valence of one oxygen atom. Methane, the main component of natural gas, is a compound with the molecular formula CH4. It takes 4 hydrogen atoms, each with a valence of 1, to complete the valence shell of a carbon atom with a valence of 4. Atoms in a molecule attract shared bonding with electrons in varying degrees depending on the element. The attraction of a particular atom for electrons of a covalent bond is called its electronegativity. The more electronegative an atom is, the more strongly it pulls shared electrons towards itself. In a covalent bond between 2 atoms of the same element, the electrons are shared equally because the 2 atoms have the same electronegativity. The tug of war is a standoff. Such a bond is called a covalent bond. For example, the single bond of H2 is nonpolar, as is the double bond of O2. When an atom is bonded to a more electronegative atom, the electrons of the bond are not shared equally. This type of bond is called a polar covalent bond. Such bonds vary in their polarity depending on the relative electronegativity of the two atoms. For example, the bonds between the oxygen and hydrogen atom of a water molecule are quite polar. Oxygen is one of the most electronegative elements, attracting shared electrons more strongly than hydrogen does. In a covalent bond between oxygen and hydrogen, the electrons spend more time near the oxygen nucleus than the hydrogen nucleus. Because electrons have a negative charge and are pulled towards oxygen in a water molecule, the oxygen atom has partial negative charges and the hydrogen atom has partial positive charges. Not all salts have equal numbers of cations and anions. For example, the ionic compound magnesium chloride, MgCl2, has 2 chloride ions for each magnesium ion. Magnesium, 12 Mg, must lose 2 outer electrons of the atom to have a complete valence shell, so it has a tendency to become a cation with a net charge of 2 plus Mg2 plus. One magnesium cation can therefore form ionic bond with 2 chloride anions. The term ion also applies to entire molecules that are electrically charged. For example, in the salt ammonium chloride, for instance, the anion is a single chloride ion, but the cation is ammonium, a nitrogen atom covalently bonded to 4 hydrogen atoms. The whole ammonium ion has an electrical charge of 1 plus because it has given up 1 electron and is just 1 electron short. Environment affects the strength of ionic bonds. So weaker interactions with and between molecules are also central to the chemistry of life, contributing greatly to the emergent properties of life. Many large biological molecules are held in their functional form by weak interactions. In addition, when 2 molecules in the cell make contact, they may adhere temporarily by weak interactions. The reversibility of weak interactions can be an advantage. 2 molecules can come together, affect one another in some way, and then separate. There are several types of weak chemical interactions, and these are hydrogen bonds and van der Waals interactions. So hydrogen bonds are amongst the weak chemical interactions. Although saying this, they're essential to the chemistry of life and they deserve special attention. When a hydrogen atom is covalently bonded to an electronegative atom, it is said the hydrogen atom has a partial positive charge that allows it to be attracted to a different electronegative atom with a partial negative charge nearby. This non-covalent attraction between a hydrogen and an electronegative atom is called a hydrogen bond. In a living cell, the electronegative partners are usually oxygen or nitrogen. So van der Waals interactions are basically when even a molecule with non-polar covalent bonds may have positively and negatively charged regions. Electrons are not always evenly distributed at any point. They may accumulate by chance in one part of a molecule or another. The results are ever-changing regions of positive and negative charge that enable all atoms and molecules to stick to one another. These van der Waals interactions are individually weak and occur only when atoms and molecules are very close together. However, when many such interactions occur simultaneously, they can be powerful. Van der Waals interaction, hydrogen bonds, ionic bonds in water, and other weak interactions may form not only between molecules, but also between large parts of a molecule, such as a protein or nucleic acid. The cumulative effect of weak interactions is to reinforce the 3D shape of the molecule. So in terms of molecular shape and function, we need to consider the effects of certain drugs that are of a particular shape, and these good examples are morphine and heroin, which are both derived from opium. Opiates basically relieve pain and alter mood by weakly binding to specific receptor molecules on the surface of brain cells. Endorphins are signaling molecules made by the pituitary glands that bind to receptors, relieving pain and producing euphoria during times of stress, such as intense exercise. Opiates have similar shapes to endorphins and can bind to endorphin receptors in the brain. That is why opiates and endorphins have similar effects. The role of molecular shape in brain chemistry illustrates how biological organization leads to math between structure and function.